Hello class, this is Ms. Riggins with today's video on section 2.6 in the textbook on differentiability. It is your responsibility as you're watching the video to take down notes, important information, as well as writing down any questions. Feel free to pause, review, or replay the video multiple times until you understand. And of course, don't forget to write down your video summary and submit the online whisk form before class. Let's go ahead and begin. So we've been talking about derivatives, and so what does it mean for a function to be differentiable at a point x? Well, the function is differentiable at the point x if the limit as h approaches 0 of this difference quotient exists. And we all know this, we've been dealing with this for about a week or so. But if the limit does not exist, then we say that the function is not differentiable at x. If the function is not differentiable at x because that limit does not exist, that means the function is not differentiable on the interval that contains x, or the function is not differentiable over the entire domain. But if the limit does exist, then we say that the graph of f has a non-vertical tangent line at x, which means that the value of the limit would be the slope of the tangent line, and that would be the derivative of f at x. But let's take a look at a situation where the derivative does not exist. And there's actually three types of situations where the derivative does not exist, and that's because the limit would not exist of this difference quotient. So let's take a look. Functions are not differentiable at a point if one of these three situations occur. If the function is not continuous at that point, the derivative does not exist. I don't know why I can't draw a straight line. So in this case, as we can see here, that at x equals 3, the function is not continuous. So therefore, the limit as x approaches 3 of any difference quotient is not going to be equal to it. There's not going to be a limit there. So that would imply that the limit, so therefore the function is not differentiable at that point. Another situation is when the graph has a sharp corner at that point. And we call it or a cusp, corner or a cusp. So right here, the limit does not exist of the difference quotient, and let's just review the difference quotient, is because as we're looking at the slope of the tangent line lines, as we're coming from the left, the slope of the tangent lines seem to be decreasing, but as we go from the right, the slope of the tangent lines seem to be increasing. Sorry, I'm confusing myself. I think what I said was right. So as we're coming from the left, the slope of the tangent line, and this is a line, so the slope is negative, but as we're coming from the right of the point 2, the slope is positive. So therefore we're going to have two different limits coming from both sides, so therefore the limit would not exist, so therefore the derivative would not exist at that point, okay, as far as the slope of the tangent line. And then the last situation is when the graph has a vertical tangent line. Now that's a little bit tricky because you may say, like, what does it mean to have a vertical tangent line? Well, here at this point right here, if I try and draw a tangent line at this point, even local tangent line, it's going to look like the tangent line should be very much a vertical line. And of course, it's going to be almost impossible to draw that accurately where it's a tangent line, but that's the closest tangent line would be a vertical or almost vertical line, and as you can see here, that would mean that the change in x, or the change in h, would be very, very, very small, which would mean this function here would be very, very, very large. And so therefore we cannot have a limit at this point for the slope of the tangent lines, as we see. Okay, now I want to clarify these functions, with the exception of the first situation, but these graphs do have limits of the function at x equals 1 and the limit of the function at x equals 2, but it's not differentiable at x equals 1, 2, and of course at 3. So we're going to look at theorem 2.1, and theorem 2.1 says that if f is differentiable at a point x equals a, then f of x is also continuous at x equals a. Okay, and so for those of you who wanted me to do more examples of proving, we're going to prove this. So let's take a look at the proof. First, we start off with the if statement and assume that that's true. So let f be differentiable at a point x equals a, but of course x does not equal a. We're just considering that since f is differentiable at the point for x is equal to a, but we of course understand that x is not equal to a. All right, so by the definition of derivative, then since it is differentiable at a, then f prime of a exists, and that can be found by calculating the limit as x approaches a of f of x minus f of a over x minus a. Now I know you're saying, why didn't you use the h approaches 0 one, and we're going to see why in a little bit later. So we're going to do a little math trick, because we really want to be able to show that f is continuous at a. And in order to do that, we're going to need to show something about limits involving f of x and f of a. So if I just take a look at f of x and subtract it from f of a, I can multiply both the numerator and the denominator by x minus a times x minus, and divided by x minus a, okay? So this really is a little trick that we're doing to set things up. Once we've done that, then let's take the limit of both sides. Since these two statements are equal, then their limits should also be equal. Okay, so going back to our section 1.7 and our properties of limits, we know that we can apply some algebraic steps to get what we want. So let's take the limit of, taking the limit of both of the right side, we see that the product of the limits is equal to the limit of the products. So we take the each product and separate it and take the limit of that. And what we can see is as x approaches a, x minus a, the limit as x approaches a of x minus a is going to be 0. And then this right here is exactly the definition of the derivative of f at a, as we saw earlier. And we know that this is actually a value, since our supposition was that the derivative of f exists at a. Okay, so but since this is going to be equal to 0, then it doesn't matter what the value is of f prime at a, the limit of f of x minus f of a is going to be equal to 0. Well, if the limit of f of x minus f of a as x approaches a is equal to 0, then that must mean that the limit as x approaches a of f of x is f of a. Okay, and therefore that means that f is continuous at this point, because as x approaches a, the limit exists, and that limit is exactly f of a. All right, so there's our proof. In summary, we talked about situations where the derivative of a function at a point would not exist, and we also proved where differentiability at a point implies continuity. In preparation for the upcoming activities and independent practice assignments, as well as skills tests and video assessments, I suggest you review to make sure you understand the definition and the meaning of limits, continuity, and differentiability. They both use a lot of similar different things. They use continuity and differentiability involve limits, and they involve differentiability, and non-differentiability involves limits of a particular quotient function. So make sure that you know the difference between the 2 and 3, and don't confuse the definitions, because some of them are very similar and they involve one another. And as maybe extension, start thinking about how you apply differentiability or lack of differentiability to the second derivative, because remember, the second derivative is as well a derivative of a function too. And so there may be situations where a function would be differentiable, but would not be differentiable at the second derivative. Okay, that's it. See you in class.